Greetings, calculus students. This lecture will be on the inverse trig function derivatives. This first page is a review of what inverse trigonometry is. Looking at this unit circle, focus on this angle of pi thirds radians, or 60 degrees. We know that the sine of this angle will be the second coordinate, giving us this statement. So regular trigonometry inputs an angle into the trig function, and the output is a ratio of sides, in this case opposite over hypotenuse. Well, inverse trigonometry does the reverse. Recall that inverse, or you can also say arc trig functions, they input a ratio of sides and output the unique corresponding angle within a certain window of angles. Give the range of each inverse trig function below. Using this as an example, the inverse sine, or you can also say arc sine, of this ratio should output the angle at which the sine is that ratio. However, we want inverse trig functions to output unique angles. While it is true that the sine of 60 degrees is radical 3 over 2, it's also true that the sine of 120 degrees is radical 3 over 2. But we don't want the arc sine to output more than one angle. To ensure that we get a unique angle back when you use an inverse trig function, we must limit the range of angles allowed. For arc sine, that range will be, in radians, from negative pi halves to pi halves, or in degrees, negative 90 degrees to 90 degrees. That sweeps out this portion of the unit circle, so including quadrants 4 and 1. And if you're looking at quadrant 4, the angle you give must be a negative angle to get there. Quadrants 4 and 1 will be the range of these three inverse trig functions. I'll just give answers now in radians. So for inverse cosecant, the range will be from negative pi halves up to, now we have to exclude 0 because the sine of 0 is 0, therefore the cosecant of 0 is undefined. So we have to describe quadrant 4 using this interval, excluding 0 but including the negative pi halves, union, and then the first quadrant, 0 to pi halves. Now for inverse tangent, keep in mind that the tangent of negative pi halves and pi halves is undefined. So the range of the inverse tangent will be an open interval, negative pi halves to pi halves, giving us again quadrants 4 and 1. Now for arc cosine, the range for arc cosine will be any angle from 0 radians up to pi radians. That means the outputs of arc cosine will always be somewhere in this range of angles, so quadrants 1 and 2. For arc secant, it'll be similar, except that at pi halves, the secant is undefined, so we have to exclude pi halves from this range. So we go from 0 to pi halves, parentheses, union, parentheses, pi halves up to pi, giving me quadrants 1 and 2, but excluding the angle pi halves. And for arc cotangent, cotangent is undefined at 0 and pi, so we're going to have an open interval for its range, again, quadrants 1 and 2. These three inverse trig functions focus on the top half of the unit circle, giving positive angles somewhere in the first or second quadrant. If possible, find the output of each function. Use the unit circle when possible and technology when necessary. Let's begin with arc sine of 1/4. For arc sine, we limit our view to the fourth and first quadrants. So we're trying to find an angle for which the sine is positive 1/4. That means we should not look at the fourth quadrant because the sine is negative in the fourth quadrant. So I'm trying to find an angle somewhere in the first quadrant where the sine is 1/4. So quickly scan the y-coordinates, 1/2, rad 2 over 2, and rad 3 over 2, and 1/4 is not present here. But 1/4 is also half as high as 1/2. So on the unit circle, there would be a point somewhere around there where the y-coordinate is 1/4. And the question is, what is the measurement of this angle? You cannot assume that it's half of 30 degrees, but because we're trying to find an angle that's not one of these standard angles on the unit circle, I'll have to reach for a calculator. Using Desmos, type in arc sine of 1/4. Click on the wrench to see what mode you're in, and currently we're in radian mode. Let's switch to degrees for a moment. And we can see that we get about 14.48 degrees. Or switch to radians, and we get about 0.253 radians. Using Desmos, you can also type in, instead of arc sine, sine to the -1 power. This is an indication of doing an inverse sine function. Desmos recognizes both notations. For the next one, arc cosecant of -0.2. The range of arc cosecant is still quadrants 1 and 4, so we're looking for an angle somewhere in these quadrants where the cosecant will be -0.2. Well, the cosecant is negative only in the fourth quadrant of these two options, so I'm looking for a negative angle. I'll call this angle alpha. The cosecant of alpha will be -0.2, which is -1/5. That means that the sine of alpha would be -5 because they're reciprocals of each other. But the lowest the sine can be is -1, meaning that this is impossible, suggesting that it's not possible to find the arc cosecant of this number. So we have a does not exist, confirming with technology. The arc cosecant of -0.2 is undefined. This suggests that all of these inverse trig functions have domain restrictions as well. In the case of arc sine, x must be somewhere between -1 and 1. For arc cosecant, x must be less than or equal to -1 or bigger than or equal to 1, which is why arc cosecant of -0.2 is not possible. For arc tangent, x can be anything. So I'll say x can be an element of any real number. The domains of the other three are identical to these first three domains. So in some cases, you can only find an inverse trig function of a certain kind of number, and when possible, you get a unique angle in a limited range. Okay, moving on. Arc tangent of -5. So we are looking for an angle in quadrants 4 or 1 where the tangent would be -5. Well, the tangent is positive in the first quadrant, so again, I know I'm looking for a fourth quadrant answer here. Whatever the angle is, the tangent of that angle should be -5. Well, given the angles on the unit circle, you can find tangent by doing sine over cosine. So at this angle, we would have -1/2 divided by rad 3 over 2, and that does not produce -5. So this angle is not the angle I'm looking for. In fact, none of the angles on the unit circle will be appropriate. So this is another case where I have to use technology to find an answer. And in degree mode, we get approximately -78.69 degrees. That is a fourth quadrant angle. Or in radian mode, we get approximately -1.373 radians. Right, the next example, arc cosine of -rad 3 over 2. Arc cosine has a range from 0 to pi, so somewhere in quadrants 1 and 2. But the cosine is positive in quadrant 1. In fact, all trig functions are positive in quadrant 1, telling me I should find an angle somewhere here in quadrant 2. And we want the cosine of that angle to be -rad 3 over 2. Well, this happens to be an angle on our unit circle. Look to the first coordinate, and I see that we have an angle of 150 degrees, or 5 pi 6 radians, at which the cosine is -rad 3 over 2. So we get an exact answer, 150 degrees, or an exact answer of 5 pi 6 radians. Confirming with technology and in degree mode, we get the 150. In radian mode, we get a decimal answer. Let me type in 5 pi 6, and we confirm that the decimal answer matches 5 pi 6. So it's always better to give an exact answer when you can, instead of a rounded decimal. The next one, the arc secant of -2. Again, we're interested in quadrants 1 or 2, but the secant is positive in quadrant 1. So once again, I'm focused on quadrant 2, and the angle I'm looking for, whatever it is, I want the secant of that angle to be -2, which means that the cosine of that angle would be the reciprocal -1/2. This also happens to be a location on my unit circle. The cosine is -1/2 at the angle 2 pi 3 radians, or 120 degrees. That means the secant of this angle is -2. So we get 120 degrees, or 2 pi 3 radians. And the last one, the arc cotangent of -1. Again, my answer will be somewhere in quadrants 1 or 2, but in quadrant 1, cotangent is positive. So once again, I'm looking for an answer in quadrant 2. We'll call the angle I'm looking for alpha. We know that cotangent of alpha would be -1. And cotangent of an angle is cosine divided by sine. So if I take the first coordinate, which is cosine, and divide it by the second coordinate, which is sine, I'll get cotangent for that angle. Therefore, at this angle here, the cotangent would be -rad 3, which is not -1. However, at the angle 3 pi 4ths, the cotangent is -rad 2 over 2 divided by +rad 2 over 2. That does simplify to -1. So this is the angle that I am looking for, 135 degrees, or 3 pi 4ths radians. So here's a quick review of inverse trig. Sometimes the unit circle is helpful in evaluating an inverse trig function, and sometimes the unit circle is not helpful, and we need to resort to technology. Okay, now we're going to focus on the graphs of some of these inverse trig functions, and then the derivatives. Moving on to the next page. Given the graph of the function below, predict the graph of its derivative. Then use implicit differentiation to find the derivative. Use technology to graph the derivative and compare with your prediction. All right, the function in question is y equals the arc sine of x. You can see that its domain, it's limited from -1 to 1, as we said on the previous page, and its range is -pi halves to pi halves, as we stated on the previous page. Now, to predict the graph of its derivative, imagine a point somewhere on the curve, such as the orange point, imagine the tangent line at that point and its slope and assign a numerical value to the slope. So currently it would be some large positive number. Now as you imagine the point moving, imagine the tangent line changing. It's becoming less steep, so less positive. And right here seems to be the least steep portion of our graph. After that, the tangent lines that I'm imagining get steeper and steeper and steeper as we move along the curve. Here I'm now using technology to show what I was imagining. At this point, the tangent line has a slope of about 4.1. And as the point moves, we can see that the slope is decreasing. At the origin, the slope is as low as it gets, 1. And then as we continue to move, the slopes increase again, getting steeper and steeper. Now notice as I get closer and closer to the right side of this graph, the slope becomes very steep, getting closer to a vertical tangent. Also true as I get closer to the left end of this domain. The slopes also get very large and positive, getting closer to infinity or a vertical tangent. In our notes at the origin, it appeared the slope of the tangent line was 1, so we expect the derivative to have an output of 1. And 1 is about right here, a little bit more than pi-fourths. And then as we move along the curve in this direction, the slopes just approach infinity. So we expect the outputs to just go up and get closer to infinity following an asymptote. And then as we go backwards along this curve, the slopes also just get steeper and steeper and positive, also approaching infinity, so following an asymptote. So whatever the derivative is, I expect its shape to be something like this. Let's confirm. Okay, if we have the function y equals arc sine of x, the meaning of these symbols would be the input of the arc sine would be a ratio, in this case, some opposite over hypotenuse, because that is how you calculate sine of an angle. And the output is an angle. If I rewrite this using regular trig, then I would have that the sine of that angle y would equal this ratio x. Now the reason I want to do this is because I can now use implicit differentiation because I know how to differentiate regular sine. So I'm going to differentiate both sides with respect to x, meaning that we treat this y as an implied function of x. So I'll have to use the chain rule when I differentiate sine of y. Derivative of sine is cosine, and then chain rule times y prime. And then derivative of the other side. The derivative of x with respect to x is just 1. So this tells me that y prime will be 1 over the cosine of y. But I'd like to express my answer here in terms of x. I don't want a y variable in my derivative. The way we're going to do that is to take the original statement and from it make a reference triangle. It's a right triangle. We want the sine of y to be x. Now remember, in regular trig, this y is an angle. So in my labeling, I would put y as an angle measurement. And we want x to be the ratio of sides. In this case, opposite over hypotenuse. So just imagine that x being over 1, and then I can identify that x should be the opposite and 1 should be the hypotenuse. So here I have a reference triangle where it's true that the sine of y would be x. And now I can use the Pythagorean theorem to find the other side, to complete the reference triangle. I'll call it b for now. So we know that b squared plus x squared should equal 1 squared. So b squared is equal to 1 minus x squared. So b is equal to the square root of 1 minus x squared. So I now have a complete reference triangle, and I can use it to establish what the cosine of y is. The cosine of y is adjacent divided by hypotenuse. So that gives me radical 1 minus x squared, and then divided by 1, which I won't bother writing. So in summary, the derivative of the arc sine, or inverse sine, of x is equal to 1 over the square root of 1 minus x squared. In Desmos, I typed that function, calling it y, and sure enough, it makes the graph that we predicted. Okay, next page. Given the graph of the function below, predict the graph of its derivative, then use implicit differentiation to find the derivative, use technology to graph the derivative and compare with your prediction. So same instructions, but we are now working with y equals arctangent of x. You can see that the graph has two horizontal asymptotes, one at negative pi halves and one at positive pi halves. The domain is all real numbers, and the graph is defined for every x-coordinate, but the range is limited. The outputs have to be somewhere between these asymptotes. Now imagine a point somewhere on the curve. Imagine the tangent line. It would be a small positive slope. And as this point moves, the tangent lines get steeper and steeper and steeper, reaching a maximum steepness right here. If I draw the tangent line, it appears to have a slope of about 1. And then after that, the tangent lines become less steep, but still positive, getting closer and closer to being horizontal, so closer to 0. We can see that the slopes increase, are positive, get to a maximum of 1, and then start to decrease again as the graph flattens out, and the slopes will get closer and closer to 0 the further to the right we go. So in my notes, I expect the graph of the derivative to have an output of 1 when x is 0, and then moving off to the right, I expect those slopes to drop and get closer to 0. Same thing off to the left. So I expect a derivative graph to look something like this. Let's confirm. Again, x represents a ratio. In this case, it would be opposite over adjacent because that's what tangent gives, and y represents an angle. Writing this in terms of regular trig, we would have that the tangent of that angle y will give us x. And now we differentiate both sides with respect to x. The derivative of tangent y will be secant squared of y, and then chain rule times y prime is equal to, and the derivative of x is just 1 again. So y prime is 1 over the secant squared of y. Next, I'll make a reference triangle using our first statement, tangent y is equal to x. So y is an angle, and we want the tangent to be x. Well, tangent is opposite over adjacent, so I'll put opposite x adjacent 1. And then we have a hypotenuse, so I'll call c, that I need to find. Pythagorean theorem gives 1 squared plus x squared must equal c squared. So c must be the square root of 1 plus x squared. This does not simplify. Be careful you don't just say 1 plus x. So I have a complete reference triangle. Well, secant would be hypotenuse divided by adjacent. So in my formula, the secant of y will simply be the square root of 1 plus x squared, and then divided by 1, which I don't need to write. But then we need to now square that. So here's the secant squared of y. And so we get 1 over 1 plus x squared. Using technology, here's the graph of our 1 over 1 plus x squared. It gives a graph of the derivative in orange that matches our prediction. And as x changes, the slopes of the tangent lines to the black curve are the outputs of the orange curve, the derivative function. So we've confirmed that the derivative of the arctangent of x is equal to 1 over 1 plus x squared. Now, give the equation of the tangent line at x equals 1. I'm going to hide our predicted graph to declutter this image. When x is 1, we have a point right here and some sort of tangent line at that point. Okay, so we need to know the coordinates of this point. The x-coordinate is 1, and the y-coordinate I'll call y sub 1. And we need to know the slope of this line, which I'll just call m for now. Let's use function notation. So we have f of x equals arctangent of x. So the y-coordinate we're after can be found by plugging 1 into the function. So it's the arctangent of 1. So we're trying to find an angle at which the tangent is 1. That angle will be in the first quadrant, and the angle is on the unit circle. It's pi fourths, confirmed by this graph. Now the slope will be found by plugging the same x-coordinate but into the derivative function. And of course, the derivative of arctangent is 1 over 1 plus x squared. So plug 1 into that, and we get 1 over 1 plus 1 squared, winding up giving us 1/2. So now we use point-slope form to create the equation. The y-coordinate was pi fourths. The slope was 1/2. The x-coordinate is 1. Distribute the 1/2, and then add the pi fourths. And we have our equation in point-slope form. Graphing it with technology, we confirm that this answer does in fact appear to be the tangent line to the curve when x is 1. Okay, next page. Use implicit differentiation to find the derivatives of the remaining inverse trig functions. I plan to work through these rather quickly. Convert to regular trig. We get cosine y must be x. I'll go ahead and make a reference triangle now. The angle is y, and the cosine is x. Well, cosine is adjacent over hypotenuse. So we'll get x is the adjacent, and 1 is the hypotenuse. Pythagorean theorem will give us the other side must be the square root of 1 minus x squared. Now I'll differentiate both sides with respect to x. The derivative of cosine is negative sine of y times y prime is equal to, and the derivative of x with respect to x is 1. So y prime is equal to negative 1 over sine y. Well, the sine of y is opposite over hypotenuse. So the sine of y is simply the square root of 1 minus x squared. Here in technology is a graph of arc cosine of x in black and its derivative as we just found it in orange. You can see, given the graph of arc cosine, that the slopes must all be negative and extremely negative at the endpoints as the tangent lines approach verticality. Okay, arc secant. We know that the secant of y therefore must be x. So reference triangle, the angle is y and the secant must be x. Well, the secant is hypotenuse over adjacent, giving us the square root of x squared minus 1 as the other side. Take a moment and confirm that. Now differentiate both sides with respect to x. The derivative of secant is secant y tangent y, and then chain rule times y prime equals, and then the derivative of x is 1. So y prime is equal to 1 over secant y tangent y. Well, using our reference triangle, the secant of y is just hypotenuse over adjacent, so just x, and the tangent of y is opposite over adjacent. So we get y prime must be equal to 1 over secant of y is just x, and tangent of y is just the square root of x squared minus 1. Now, using technology, the graph of arc secant is given in black, and the graph of the derivative as I found it is given in orange. There is an inconsistency here, though. Notice that for either portion of the black curve, the tangent lines should all be positive, yet the outputs of the left branch of the derivative are negative outputs. This is an inconsistency. It turns out, because of the technicality that the angle y could also be in the second quadrant, that we need to put this x here in absolute value, which will guarantee that the outputs of our derivative will always be positive as expected. We now see we have a derivative function that has only positive outputs, which corresponds to the fact that the black function only has positive sloped tangent lines. Now let's look at arc cosecant. If y is equal to the arc cosecant of x, then the cosecant of y must be x. So here's our reference triangle. Cosecant is hypotenuse over opposite. So the hypotenuse would be x, the opposite would be 1. And Pythagorean theorem would give us the adjacent as square root of x squared minus 1. Now, implicit differentiation, the derivative of cosecant y will be negative y prime, chain rule, times cosecant y cotangent y, and the derivative of x is just 1. So y prime will be negative 1 over cosecant y cotangent y. Using my reference triangle, the cosecant of y is hypotenuse over opposite, so x, and the cotangent of y is adjacent divided by opposite, so just square root of x squared minus 1. So we get negative 1 over x times the square root of x squared minus 1. Using technology, the graph of arc cosecant is given in black, and the derivative as I found it is given in orange. Again, notice that we have an inconsistency. For either portion of the black curve, the tangent lines ought to have negative slopes, yet our derivative, the left branch of the orange function, has positive outputs. That's a contradiction. This has to do with the technicality that the angle y could be a negative angle in the fourth quadrant, and without going into the details, the fix is to put absolute value bars on this x like before. This will ensure that our derivative is also correct for the fourth quadrant outputs. And now finally, if y is equal to arc cotangent of x, then that means that the cotangent of y needs to be x. So making my reference triangle, cotangent is adjacent over opposite, so the adjacent needs to be x and the opposite needs to be 1. Pythagorean theorem will give me that the hypotenuse must be the square root of 1 plus x squared. And now differentiate using implicit differentiation. With respect to x, the derivative of cotangent is negative cosecant squared of y, and then chain rule times y prime, which I'll put right there, is equal to, and the derivative of x is just 1. Solving for y prime, we get negative 1 over cosecant squared of y. Well, cosecant is this hypotenuse divided by 1. So in other words, the cosecant of y is just the square root of 1 plus x squared. So y prime will be negative 1 over square root of 1 plus x squared. But now I need to square the cosecant of y, so I must square that square root, which will cancel it, giving us this derivative. Using technology, the graph of arc cotangent is given, and its derivative. Notice that the slopes of all the tangent lines to the black curve will have negative slope, as indicated by those negative outputs of the orange graph of the derivative. All right, notice a few things before we move on. Backing up a page, we saw that the derivative of arc sine was 1 over the square root of 1 minus x squared. And notice that the derivative of arc cosine is the same thing but negative. Backing up a page, the derivative of arc tangent was 1 over 1 plus x squared. And the derivative of arc cotangent is the same thing but negative. And finally, notice the derivative of arc secant is 1 over absolute x times square root of x squared minus 1, and the derivative of arc cosecant is the same thing, but negative. Okay, moving on. Express the function as a composition y equals f of g of x, where y is this function, then use the chain rule to find its derivative. So now we're doing a composition. We have a function plugged into an inverse trig function. Well, the composed function g is easy to identify as the argument here. It is 4x cubed plus 1, and that's being plugged into the f function, which is simply the arc sine of x. Sure enough, if you take g and substitute it in for the x and f, we've confirmed that the result will be this y function. So we'll use the chain rule, which means I'll need the derivatives of f and g. The derivative of g is using the power rule, 12x squared. The plus 1 goes away. And the derivative of f, using the rule we just developed, is 1 over the square root of 1 minus x squared. Now the chain rule says that y prime, therefore, will be f prime of g times g prime. So we're going to take the g function and plug it in for all the x's in f prime. So we get 1 over square root of 1 minus, and replace that x with 4x cubed plus 1, and that needs to be squared. And then multiply by g prime, and g prime is just 12x squared. And I'll just put that in the numerator. So in summary, if you call the argument u to stand for some function, this would be a u here. Up top would be u prime. This allows me to create a generalized inverse sine rule. So here we have u representing any function. We're differentiating with respect to x. The derivative of arc sine is 1 over the square root of 1 minus the argument u squared, and then chain rule times u prime, which I'll just put in the numerator. Arc cosine will be the exact same, but negative. Arc tangent, its derivative was 1 over 1 plus the argument squared, and then chain rule times u prime, which I'll just put in the numerator. Well, jumping over to arc cotangent, this will be the exact same answer, but negative. Let's do arc secant next. Its derivative was 1 over the absolute value of the argument times the square root of the argument squared minus 1. And then chain rule, multiply by u prime, which I'll put in the numerator. And then finally, the derivative of arc cosecant will be the same, but negative. These form the 6 generalized inverse trig rules that you'll want to know moving forward. Let's do 2 quick examples. Find the derivative of each function below. Here we have a constant times a function, so that negative 3 will just stay. And we're doing arc tangent of some function of x. And x is our independent variable. So I'll think of that as my u. And I know, therefore, that my answer should be the negative 3 will stay. We'll get u prime in the numerator over 1 plus u squared. That's just this rule with a negative 3 being multiplied to it. And since u is the square root of x, I know that u prime is 1 over 2 square roots of x, and we divide by 1 plus the square root of x, and that needs to be squared. Well, simplifying this complex fraction, you can multiply the top and bottom by 2 rad x. We have negative 3 over 2 rad x times just 1 plus x. And here's a nice simplified version of our derivative. That's not a complex fraction. In this next example, t is the independent variable. This time I have a coefficient that's not a constant, it's a t, times an inverse sine of 5t. So I need to use the product rule in this one. Split right here. I'm going to use v and w as my 2 representations of the factors. So we'll get the derivative of v. So the derivative of t with respect to t is just 1 times w, which is arc sine of 5t. This is my v prime times w. And then plus v, which is t, times the derivative of arc sine of 5t. Well, this 5t I'll now use it as a u in conjunction with this formula here. So to differentiate arc sine of 5t, I'll put the derivative of 5t in the numerator, which is just 5, over the square root of 1 minus, and then 5t in parentheses needs to be squared. So this t is my v, and this fraction next to it is my w prime. And I'll just do one step of simplification. So we get arc sine of 5t is the first term, plus, and then we have 5t over the square root of 1 minus, and if I remove those parentheses, I'll have 25t squared, because the 5 and t both get squared. And again, this fraction here was found by doing u prime over square root of 1 minus u squared, where u was 5t. So we had a generalized inverse trig rule nested within a product rule on this one. All right, this page wraps up our conversation on inverse trig derivatives, but there is one more page. Let's move to that. This page is a summary of all the derivative rules that we have learned up to this point. We're going to treat u and v as functions of x, so we're going to assume x is always the independent variable, and we're going to treat k, n, and b as constants. The first column will be the function y, and then we're going to fill in the formula for y prime, its derivative. So if y is a constant, then its derivative will be 0. If y is a constant times a function, then that constant will stay, so the derivative of ku is k times the derivative of u. If we have a sum or difference of two functions, then we differentiate term by term. We'll differentiate the first, and then plus or minus as necessary, and then differentiate the second. If we have a product of two functions, then we must use the product rule, u prime v plus uv prime. If our function is a quotient, then we switch to the quotient rule. Derivative of the numerator, u prime v minus uv prime, all over v squared. And if we have a composition of functions, u of v, this is the chain rule, and it would be the derivative of the outer function, u prime, composed with the inner function still, but then multiply all of this by the derivative of the inner function. To put names on these, we have the constant rule. We have constant times function. We have the sum or difference rule. We have the product rule, the quotient rule, and the chain rule. Okay, now we're going to do the power, exponential, and log rules, and these are all technically generalized or general rules because you see that we have all these u's and v's represent functions. So the chain rule is going to apply through all of these. If you have a function raised to a constant, then we used the generalized power rule. And that rule is the constant drops down, the base function stays the same, the new power is one less, and then the chain rule multiply by the derivative of the inner function. In this case, multiply by the derivative of the base. This next case is a constant b raised to a function u. This is an exponential function, so we use the generalized exponential rule. And its rule says that we repeat the exponential function, multiply by the natural log of the base, and then chain rule times the derivative of the exponent. This rule I just wrote works for any legitimate base b. The next rule is the general exponential rule, specifically when the base is e. And we basically can rewrite this, but change all the b's to e's. And in this case right here, the natural log of e is just 1, so I don't need to write it. So the derivative of e to the u will be itself times simply the derivative of that exponent. And it doesn't matter if you leave this here or if you want to write this in the front. Let's put it in the front. In fact, the ordering of these three doesn't matter either. Neither does it matter the ordering of these three. Multiplication is commutative and associative, so you can rearrange and multiply in any order. Now, u raised to the v, this was one we discussed in the last lecture. You had to use logarithmic differentiation. I'll put the result down here without further explanation, but refer to the lecture on logarithmic derivatives to remind yourself of why the following is true. If you have a function raised to the function, the derivative will be that same u raised to the v times v prime natural log of u plus vu prime over u. You can either memorize this as a formula, or you can just remember how to do logarithmic differentiation every time you're faced with a function that's not constant raised to another non-constant function. Okay, now we have general log rules. If you log base b of a function, and that function could be in or out of absolute value, it does not matter. The result will be the derivative of the argument divided by the argument times the natural log of the base. Specifically, if we're working with natural logs, then we have a general log rule specifically with base e. And the result will be this result, but change the b to e. So you have a natural log of e sitting here, which is just a 1, so you don't need to write it. So the derivative of natural log of u, or the derivative of natural log of absolute u, both cases just give you u prime over u. Here we have the generalized trig rules. If you differentiate sine of a function, you're going to get cosine of that function, and then chain rule times u prime. Derivative of cosine is negative sine of the same argument times u prime. So negative u prime times sine u. Derivative of tangent is secant squared. Keep the same argument of u, and then chain rule times u prime. Derivative of cosecant is negative cosecant of the argument u times cotangent of that same argument, and then chain rule times u prime. Derivative of secant is secant u tangent u, and then chain rule times u prime. And derivative of cotangent is negative cosecant squared of the argument, chain rule times u prime. Recall that if your regular trig starts with c, then you need to have a negative in the derivative formula. The hyperbolic trig rules, and again, these are general hyperbolic trig rules because all our arguments are u, which represent some unknown function of x. Derivative of hyperbolic sine is hyperbolic cosine of the same argument u, and then chain rule times u prime. Derivative of hyperbolic cosine is hyperbolic sine, no negative needed, of the same argument, and then chain rule times u prime. Derivative of hyperbolic tangent is hyperbolic secant squared of the same argument times u prime. The next three derivatives will all be negative. So we have negative u prime, get the chain rule out of the way, and hyperbolic cosecant derivative will give us hyperbolic cosecant of u and then hyperbolic cotangent of u. Derivative of hyperbolic secant will be negative u prime hyperbolic secant of u times hyperbolic tangent of u. And the derivative of hyperbolic cotangent will be negative u prime hyperbolic cosecant squared of u. Notice the parallels with regular trig and hyperbolic trig. There's almost perfect correspondence. The only difference is that it's these bottom three that produce the negatives in the formula. And then from this lecture, we developed these remaining 6 rules. The derivative of arc sine of u will be u prime, chain rule, over the square root of 1 minus u squared. The derivative of arc cosine will be the same thing but negative. Derivative of arc tangent will be u prime over 1 plus u squared. Derivative of arc cotangent will be the same but negative. Derivative of arc secant will be u prime over absolute value of u times the square root of u squared minus 1. And the derivative of arc cosecant will be the same thing but negative. It's the arc trig functions where the trig function starts with c, so arc cosine, arc cosecant, and arc cotangent. These are the ones that have the negative involved. Okay, this concludes our lecture today, which was on inverse trig derivatives, with the final slide of summarizing all the derivative rules that we have learned up to this point.